So I'm not sure what the average age in this room is, but if you remember over a decade ago, certainly trying to leverage emerging technologies was quite difficult. There were definitely a number of barriers to leveraging emerging technologies, such as cost. Certainly, if you wanted to use something like machine learning, there was a considerable amount of compute that you needed to be able to train a machine learning model. And then additionally, there was a considerable amount of skill that was required to be able to leverage that sort of emerging technology. What we're finding these days, at least in the past 10 years, is that that sort of capability has become democratized. So once again, with machine learning, you're able to leverage the power of the cloud and ephemeral compute to be able to train a machine learning model for an effective cost. And then additionally, you're able to leverage managed machine learning capabilities such as Amazon Recognition or Amazon Lex to be able to use those capabilities without requiring that specialist skill set. What we're finding over the past year or so since the release of AWS Robomaker was a very similar case, and that is that the costs that are required have significantly reduced with things like ephemeral compute to be able to run scaled out simulations, but additionally things like cheaper 3D printers to allow for better prototyping, and more iterations of prototyping have come about. And then additionally, the skills required to be able to build a robotic application certainly aren't deeply required as before. So for instance, being able to leverage the robot operating system certainly allows you to leverage a lot of what the open source community has already produced to be able to then integrate into your own robotic application. So my name's Bobby Kubor. I'm a solutions architect from AWS in Sydney, Australia. And with me I have Michael and Tom from NASA JPL. And over the next hour, we're going to go through a number of things that we've seen in the robotic industry over the past year or so, specifically with the release of AWS Robomaker. So what we'll do is we'll briefly go over the robot operating system, and we'll also look at AWS Robomaker. We'll do a quick overview. And then we'll start diving deeper into a number of common trends across robotic technologies, so including unmanned ground vehicles, robotic arms or manipulators, as well as drones. And then hopefully we'll have some time for some Q&A. So to begin, we'll cover AWS Robomaker. So one thing that we hear a lot from our customers is that robotic development is difficult and time-consuming. So one thing that's for certain, which we touched on before, is to build out robotic applications, you need an intelligent function, and therefore you need machine learning capabilities or skills to be able to build out that intelligent robotic capability. Additionally, many prototypes are usually required. So often you would develop multiple different prototypes and you would take them from scenario to scenario, which would be quite time consuming. If you wanted to set up a simulation environment to be able to iterate through those prototypes quite quickly, that setup would take some time, especially if it's your first time. And then once you've set that up, if you wanted to really scale out your simulations to be able to run multiple iterations in parallel, certainly the compute required would be difficult to obtain. So if you're working off a local workstation, you would usually queue a simulation after another simulation. And if you're regression testing and you've got 1,000 simulations that you want to power through, that would take considerable amount of time. And then additionally, there's duplicate effort required once you're in production, usually, to roll out your robotic application to a fleet of robots. So we heard these difficulties, and in 2018 at AWS reInvent, we released a new service called AWS Robomaker, which hoped to resolve a lot of these difficulties that we just saw. And the service is really to provide developers with a mechanism to easily create and develop and deploy robotic applications, not only in a simulation, but also in a physical environment or onto a physical robot. And so AWS Robomaker actually extends one of the most widely used open source robotic software frameworks, which is the Robot Operating System. But it also integrates a number of additional capabilities. So for instance, being able to use cloud extensions for ROS, which allows you to leverage a number of AWS services within your robotic application. So for instance, being able to use Amazon Rekognition or Amazon Lex to provide those intelligent capabilities. Additionally, we provide a development environment which is based on the Cloud9 IDE, and it's fully configured for that robotic developer experience. We provide a simulation capability, which essentially allows you to test out your robots and really scale out those simulations in parallel to collect that feedback much quicker and then be able to iterate on your development much quicker. And then we provide a fleet management capability, which allows you to roll out your updates over the air to your fleets of robotics. So as I mentioned before, AWS Robomaker extends extends one of the most widely used open source robotic software frameworks, the Robot Operating System. Now, this was founded in Stanford Labs more than 10 years ago, and it's now managed by the Opensource Robotics Foundation. ROS itself is actually a meta operating system. So it provides a lot of the capabilities that you would expect from an operating system. Things like low-level device control, message passing, and package management. So one of the really cool things about ROS is that it provides you the ability to break up your code into modular packages and then be able to share that with the open source community, or even take existing packages from the open source community and integrate it into your robotic application. So a lot of the time, you're not starting from scratch. You're able to leverage a lot of what the open source community has provided as a boilerplate. So what we'll do now is we'll just dive into a couple of different areas. The first one being unmanned ground vehicles. So we're seeing a number of common use cases. One is in warehouse logistics, so being able to ferry objects from point A to point B. And certainly you see from this picture here that this is from a fulfillment center where it's actually picking up the entire shelf and taking it to a human picker to fulfill an order. In space exploration, and I'll leave that for JPL to discuss that very soon. In agriculture, we certainly see that in the form of autonomous tractors, but also in the form of autonomous weed control. So the idea that you're able to use vision or edge inference to be able to detect a weed as you're rolling along and be able to handle that weed, usually by pushing it back into the ground, which I didn't know was a weed control mechanism until I found out about it. And then product delivery. So these guys are actually rolling around a number of cities currently being tested, and they're delivering not only takeaway, but also e-commerce products. So you might see one of these guys rolling past you on a footpath at some time. And then obviously the one that we're all quite familiar with, domestic cleaning. So this is sort of also inspired automated mopping as well as pool cleaning in a similar type of device. So one thing we have noticed with unmanned ground vehicles is definitely a shift from what was traditionally something that would follow a predetermined route to something that's able to determine its own path and be able to change that as it goes. So previously we'd see quite a bit of the automated guided vehicles, the AGVs. These were often used in fairly static environments, and they still are considerably. So if you think about a logistics warehouse or a factory where things don't change that much in terms of the environment, you're able to lay down external sensors, which could be in the form of barcodes or it could be in the form of markings along the ground. And then that provides a guidance mechanism for the robotic device to be able to follow. And it's a predetermined route. So that predetermined route, when the device encounters an obstacle, it's going to stop and wait for that obstacle to be removed. So it's a lot less flexible. And in the event that you change your environment, you would need to change where those external sensors reside. On the other hand, what we're seeing a lot more of these days is the requirement to be able to adapt to dynamic environments. So autonomous mobile robots, AMRs, are able to self-determine their own route using an existing map. They're able to find an optimized path. They're able to adapt easily to changing environments, and if they encounter an obstacle, they'll usually work their way around it. They'll find another path to get around it. So this video sort of gives you an idea of how an AMR might be able to map out its path. So what we're actually doing here is performing a task called G-mapping, and it's part of the simultaneous localization and mapping algorithm, also known as SLAM. What we're doing here is manually driving the robot around the environment and using onboard sensors such as LiDAR or RGBD cameras and odometry readings to be able to create a 2D map of the environment called an occupancy grid. And then what we're able to do then is once we've got that map created, we're able to save that and then use that to be able to perform path planning. So what's really good about ROS is the fact that this G-mapping algorithm, it's already written for you. You can simply take it and apply it to your robotic device, but you still need to dictate where the sensors are and which way they face. But a lot of the hard work is already done for you. So this sort of shows basically the same robotic device using the same map to be able to perform that path planning. So what we're actually doing here, we've dictated a specific location that we want that robot to go, and we're actually spawning these couches within the house. And you can see that the robot is able to navigate its way around them. So it's changing its path as it comes into vision of those couches, and it's able to simply change its path. So what's actually happening is we're using what's called a global planner to create that original path. That global plan is then being passed to a local planner, which is then executing that path segment by segment, and it's modifying it as it needs to see fit to be able to work its way around any obstacles. So what I'll actually do now is actually invite Tom and Mick on stage from JPL to sort of go through what they've seen over the past year or so in the robotics area.
Thank you.
Thank you.
Thank you very much. Is this thing on? Yep, it's on. So I'm now turned on officially. I'm Tom Soderstrom. I am from NASA's Jet Propulsion Laboratory, and there are no slides. Now there are slides. I am the Chief Technology and Innovation Officer for IT, and what we wanted to do is talk a little bit about what we do at NASA, and there are several JPLers here, and then Mick is going to come up and give you a challenge. So JPL, as you can see here, it's 6,000 people, roughly, and it's about $2.6 billion. So it's kind of an enterprise. And it was created in 1936 by Caltech. Anybody heard of Caltech? Caltech, pretty prestigious place, except they were starting to blow up rockets. So the professors said, okay, go out in the arroyo and blow up yourself. So that became an Army lab eventually, and it became the place that created the first US satellite. And it was sent in response to Sputnik. In 1958, we sent up the very first satellite from JPL. That was then that successful that it became moved from the Army to NASA that was just formed in 1958. So we're now a civil. We don't build weapons. We launch spacecraft and we manage them. Why do we do it? We do it to answer these questions. That's really our mission. How do we protect Mother Earth? So we have a lot of Earth science instruments that look back at Earth, trying to predict hurricanes, floods, and measure from space. You get a very different perspective. And all of the other ones here, could we divert an asteroid? And if we were not successful, would we have a place to go? So we currently have found about 8,000 exoplanets, and 29 of them are Earth-like, where they could have liquid water. So we're getting there. It just takes a little bit to get there, hundreds of years and with current transportation. So that's up to you to fix. Come up with better transportation for us. Cassini. Anybody heard of Cassini? Yeah, it was a wonderful day. It was a sad day. We had it commit suicide. It was done in 2017, and it discovered all these wonderful things. We're still getting data from Cassini well, not from Cassini, we're still analyzing the data it sent. And what happens at the end of a mission like that, it's a very big mission. Saturn is a long, long ways away. But at the end, you start experimenting. It's going to die anyway. You take risks. So we got more science those last 3 months than we had before. So taking risks, experimenting is what this is all about, what JPL is about. Hopefully that's what you are about. And we look at data. We get lots and lots of data. So 2 new spacecraft, SWAT with the French Space Agency and NISAR with the Indian Space Agency, are going to launch in a few years. And they are pumping over 100 terabytes of data per day. That's a lot of data. So it's a good thing we're using cloud computing. In fact, it's 100 times more than everything we've ever done before. So cloud is a big deal for us. So that's why we're at this conference. This is kind of fun. Anybody know what planet this is? You're right, it's not a planet. It's a moon. It's Europa. So it is a moon of Jupiter. It has more water than Earth, twice as much. It's just in an ice sheet. And there is energy. Water and energy could mean life. So we're going to go there. We're going to circle it. One day we will land. We will melt or drill into the ice lakes that have been there for 4 billion years and maybe find microbial life. So if we do that, that's a big deal. So a year ago, anybody at reInvent a year ago? Raise your hand. Okay. We simulcasted landing of InSight on Mars. And we have detected Mars quakes so far. We didn't know they existed. We found about 25 of them. They're milder than the Earth, but it proved that Earth and Mars are not the same. They're not built the same. And we're also sending a little mole down, 15 feet. Well, it made it about an inch. Hit a big rock, figured out how to pull it out, and it's now trying to get down again. So things happen. This is not Death Valley. It is the surface of Mars, and it's very dry. But we have found that the conditions for life were there, but we have not found if there was actually life. So we're sending out a new one called Mars 2020. For now, there's a test out across the world to name it, come up with a better name. It's usually by kids, and we will find out what the new name is. AWS is a co-sponsor of that effort. So it will have bigger wheels than the current rover. It is called Mars 2020, and it will launch when? 2020. And it has new instruments inside its belly to try to figure out, is there really life on Mars? No, or was there life on Mars? It's also going to drill into the rocks and store it in a little canister and drop it behind. It's going to litter on Mars. And then a future mission, that's actually a real mission called Mars Sample Return, will come, land, the little rover will go out, scoop up those, put it into a ascent vehicle that shoots it up to orbiter that takes it back to Earth. So we will litter and then we'll clean it up. It will have a buddy. This is another experiment. It's a helicopter on Mars. There's 1% of Earth's atmosphere on Mars. So it's like flying a helicopter at 100,000 feet on Earth, which is impossible. But we figured out how to do it, and it has a flight time of a whooping 3 minutes. Then it has to come back and recharge. But this is robotics. This is starting to change and experiment your way through. And what does this mean for you? Well, what we wanted to do, I'm going to invite Mick Cox up to talk about something new we created called the Opensource Rover. We wanted to give back to the community, so we built a rover that looks like the big rover, but it's open source, and it's meant for scientists, engineers, and programmer students to experiment with, students of all ages. So Mick,
Sure.
Take it away.
Thanks, Tom.
Thanks.
So as Tom mentioned, my name is Mick Cox, and I manage JPL's Open Source Rover project, which is what I'm here to talk to you today about. Everything on Mars, obviously, that roves around uses something called a rocker bogie suspension system, so 6-wheel drive in the suspension system, and then we have corner steering. We wanted to take that same drive system that we know is really good at driving over rocks and take it from a 2,000-pound rover all the way down to something that you could actually build at home. So that's what the Open Source Rover is. This is a video of it driving around over some rocks. All of the components that are on this rover are available from commercial vendors, easily accessible online places, maybe Amazon, DigiKey, McMaster-Carr, common places like that, Robotics, shops, all of those places. And basically what we did is we rolled up all of the parts that it took to build this after we designed it, and we released that as open source, and then we also released a set of instructions for how to put that together into your own functioning rover. And so both of those things are available. As an example of the types of things you'll see there, these are some of our instruction sets for how to put the thing together. We're hoping that roughly around a high school robotics club or up would be able to build this, although we've even seen success with people down to third grade and other just enterprising individuals that wanted to build this in their free time, which is fantastic. We have a couple of resources that help people build this rover itself. The one on the left is our GitHub repository. That's where we keep all of the code that drives the rover, as well as that parts list that I mentioned, and the set of instructions for how to put it together. So that's on GitHub, and I'll talk about that in a second. And then on the right, we have a community forum. So this was actually something that came to us from the community and is run by the community of builders who's putting this together. And that's a place for anybody who can chat, ask questions about how to build the rover. It's a place where people can talk about the things that they want to add to it. So we want this rover that we've released to be kind of the base platform, and then see what the public can actually come up with to improve the rover and continue to feed things back, whether it be maybe solar panels on it, new scientific instruments that they can put on it, a robotic arm, which we saw and added on stage last year to help announce Robomaker's release. The community forum is a really good place for all of that. The builders community, we announced this about a year ago, and it's already a global phenomenon. We're really excited about this. We have people in Turkey who are struggling to get batteries from the vendors that we suggested and other things like that, but it's been really fantastic. We've had monthly calls with our rover community over the last couple of months. So that's US and outside, just to kind of chat about where people are in the build, field questions. So it's been a really positive, supportive community, which is excellent. And this slide for the developers in the room is something that I really like showing. So we're at somewhere around 6,000 stars on GitHub right now, which I'm proud of. But the thing I'm really proud of is that we've merged 22 different pull requests from the public on something that is really like half software and half hardware. And it also includes documentation, a lot of those things too. So these are 22 improvements that the public has come up with that they've contributed back to us. And one of those even includes a substantial rework of the whole suspension system, the corners. They replaced motors, updated all the documentation, all the 3D models. It was really fantastic to be a part of that. So if you're interested in getting involved in this project, our website is opensourcerover.jpl.nasa.gov. This site has all the information about the project itself. If you go there, you can have some fun driving around a model of Curiosity. I spend an embarrassing amount of time when this website came out just driving it around in circles. It's a lot of fun. If you have an Xbox controller and plug it into your computer, you can drive it around that way too. That's how we control our rover, the real open source rover. But then it also has a lot of different information about the rover itself. So if you want to figure out if this is a project that's good for you, right now the bill of materials is about $2,500. So again, we're looking for like a robotics team. It's a lot cheaper than like a first robotics competition robot would be, but this is kind of my first robotics type of project. But the reason that I'm talking to you today about this project in a Robomaker session is the following, and that, as I mentioned, this is an innovation platform that we're trying to add different things to over time. One of the things that we thought we would see really quickly upon release was a self-driving and autonomous driving capability, and we have not yet seen that. So in order to help that along, we're announcing a self-driving rover challenge. It opened yesterday and will run until February 21st. And basically the idea is we're going to give you a simulated Martian environment, and we're going to give you a simulated tiny little open source rover there. So the rover in simulation is about 1 meter long. That's about how big it is in real life. And it has to traverse through this 45-meter field to get to an interesting scientific object at the end. For people who know about reinforcement learning, and I'll get into that in a second, you can basically throw a lot of compute at this and actually solve that problem for you. And I'll talk about that in a second. The rules for the challenge are fairly simple. You have a rover that starts there. We'll give you a start point, we'll give you an end point. It's your job to develop a model and a ROS package that will actually navigate the rover between those 2 points. The suspension system on our rover, like the ones on Mars, her cousins on Mars, was designed to get over some terrain, so it's okay to go over a couple small obstacles and things like that, but there are rules about what we can and can't do. There's no AAA on Mars. So we want to make sure that we don't run into anything, right? So if you make contact with an obstacle, that's going to kill your simulation, and you won't get a score for that. And you don't want to drive it off of any cliffs or anything like that either. So just really simple rules like that. This is not a reinforcement learning session, but I hope you can bear with me for about 2 minutes while I talk about why we're using reinforcement learning and specifically Robomaker to help solve this problem and do this challenge. The idea is if you're looking down, two-dimensional on the same space, the rover's over there on the right, and then our target is over here on the left. If we want to get to that place, that target, and the rover doesn't know anything else about its surroundings except for a camera field of view in front of it and a depth map or a point cloud of what's in front of it, the first naive solution might be just drive towards the goal point, right? And so if we simulate the rover driving towards the goal point for as long as we can, that might get us this white path until we hit a rock. And then we hit a rock and the simulation dies and we know, okay, we did well for a little while, but then eventually we hit a rock. So on the next simulation, we're going to drive almost as far, maybe take a turn. Maybe we go to the right. Maybe we go to the right even further, right? Run the simulation again, maybe we go to the right even further. And so as time goes on and you run the simulation tens, hundreds, or thousands of times, you're going to start to get a ton of different paths that the rover could take. And again, because we're using SageMaker and Robomaker, we can do these things in the cloud without ever needing to test this in real life on a real physical rover, which helps us make sure we don't run 1,000 different rovers into 1,000 different rocks. So if you run the simulation 100 times, 1,000 times, you might start getting many different paths, some of them which look great and some of them which will look really messy and drive backwards away from the goal. The way that we've focused this challenge and how reinforcement learning works in general is that you have a reward function that's sort of underpinning all of these simulations. And as the rover is driving towards or away from this point, that reward function is telling it whether it's doing a good job or not. So in our case, the reward function is saying, good job, you moved a little bit closer to the goal, so that's plus 1 point. You did take a little bit of energy and you spent some time driving that, so that's minus, a tenth of a point. And so that reward function is constantly the underpinning of all of these simulations that are run hundreds and thousands of times. And after a while, you'll eventually get something that looks like a solution, right? So we can get from the start point all the way to the end point. So this is fantastic. Because we have the power of simulation in the cloud, run it another 100,000 times, you might get another solution that's a little bit shorter, right? So that's the whole idea behind reinforcement learning. Each time that you're building up this model, each time that you're running this simulation, your model is learning from that and improving for the next simulation run. All of that is to say that eventually we can get to the science goal, which is the whole reason that we're doing this challenge. So as somebody who's contributing to open source, one of the most rewarding things for me is when I'm actually solving a real problem. And part of the reason that we're announcing this challenge is because we want to use this model that comes up on our actual open source rover. So the winner of the challenge will have their code committed directly to the open source rover repository itself. That'll be deployed on our rover. We have one that's roving around our campus that we're working at having it speak to people as they come up, answer questions about JPL, kind of be a tour guide. And we're hoping that we can drop this model directly on our rover that's driving around JPL. In addition to that, another really rewarding thing is a reward. So for folks who are involved in the challenge, there's some AWS credit to help offset the cost of these things, but there's also $15,000 for the winner, and then $5,000 for a runner-up prize as well. If you're interested in the challenge itself, that website is spacechallenge.tech. And you can take a second to take a photo and eventually sign up on that page. That page has all of the information about the GitHub repository with all the assets that you'll need for the challenge, a couple of links to the open source rover project as well. And so on behalf of everybody at JPL and NASA, we're really excited to see what you can come up with, and I hope to see you on the open source rover forum and then on this challenge as well. And with that, I'll hand it back over to Bobby.
Awesome. Thanks, folks. So interestingly, I think if you're already familiar with Deep Racer, you're potentially halfway there, considering you'll be well familiar with reinforcement learning. What I wanted to do before we move on to the next topic of manipulators and robotic arms is to show the sort of scale that some customers are operating unmanned ground vehicles at. So this footage may be familiar to you. You may have seen some of this footage before online, but this is essentially the inner workings of an Amazon fulfillment center. So this is a bit of a flyover of one of our fulfillment centers. And what you can see there is a number of AGVs that have essentially, they drive under these shelvings and they pick them up and then they move them to a human picker to fulfill that order. Now, at Amazon Remars mid-year, Amazon announced that we had deployed over 200,000 of these devices across multiple different fulfillment centers. So you can imagine at that sort of scale, it would be quite difficult to manage those devices, manage rolling out and updating those devices. And I guess this is where AWS Robomaker's fleet management capability can essentially address a problem like that. So AWS Robomaker's fleet management capability allows you to register robotic devices over the air and then be able to place them in a fleet and then be able to push out updates to them. They're actually using the Greengrass agent. So if you're familiar with AWS IoT's services, they use the Greengrass agent and you're able to stage rollouts. So you can potentially roll out across 10% of the fleet at a time and ensure that you don't accidentally brick your entire fleet. So you can set a failure threshold. But additionally, you can ensure that it's not currently performing an operation. So if it's in the middle of performing an operation, the last thing you want to do is roll an update out to it. So what we'll do is we'll cover robotic arms and manipulators. Certainly we see these in the areas of warehouse logistics and being able to pick up heavy objects such as pallets full of product. We see it in manufacturing with assembly, but also the handling of potentially hazardous material or the ability to do dangerous functions, potentially heavy metal welding. In space and sample collection, for instance, in surgical systems, if you've seen the Da Vinci robot, there's actually a really cool video online of one of these robotic devices doing surgery on a grape. So you can actually see it peeling back the skin. It gives you an idea of just how precise some of these devices are. And then finally, in the area of disaster response and being able to inspect packages and items that you wouldn't necessarily want to put a human being near. So once again, in the areas of manipulation and robotic arms, we're seeing, once again, a bigger shift to autonomous systems. So previously, you'd see a lot of robotic arms and manipulators doing forward kinematics. What that means is that often you would be doing the same repetitive motion that was predefined. So the device or the item that you're looking to manipulate or pick up would be placed in the exact same location, and you'd be specifying the exact same joint angles each time to be able to grasp it and then place it in another location. What we're seeing is a move to a more autonomous unit. So something that's able to visualize that object, able to determine its depth or its XYZ coordinates in relation to the robotic arm itself. It's able to reach out and grasp that object. It's able to grasp it safely, and it's able to move it around in a safe manner without colliding with anything. So to be able to provide that depth perception, we're able to use things like RGBD cameras, which are essentially able to take an image and layer depth information pixel by pixel on top of it. So if you've got a games console with a motion sensor, you'd be fairly familiar with that sort of technology. And what you can see in this screenshot here on the left-hand side, we've got what the depth sensor can see. And you can see it's actually recognized objects using OpenCV, so it's using local inference or edge inference. To be able to recognize two objects, it's drawn a green square and a red square around those objects. And then on the right-hand side, what you can see is in RViz, which is a managed component of Robomaker and used in the robotic operating system, you can see specifically where the camera is, as well as where the two objects are placed. So it's worked out those XYZ coordinates and mapped that out appropriately so that we're then able to potentially manipulate those objects. So what we're now doing would be to use the Move It framework on top of ROS, and this provides a lot of those capabilities that allow you to do manipulations, as well as motion planning, collision checking, and that sort of thing. So what we're actually able to do is once we've got those X, Y, Z coordinates for an item that we're looking at manipulating, we're able to take that, we're able to use what's called inverse kinematics, which is an algorithm that allows us to take those X, Y, Z coordinates and determine the joint angles in the arm required to be able to reach out and grasp it. And that might require multiple trajectories to be able to ensure that we avoid potential obstacles while we're doing that grasp. What you can see in that picture there is a commercial robot that's actually rolled up to something that's in front of it. It's got a depth sensor in its head, which is looking down. It's got a robot arm that's pulled out to the side, and it's basically built out what it can see in front of it in the form of an octomap. So it can see a table, which it would assume is a collision object. And additionally, it can see a number of items on that table that it might consider for manipulation. So this sort of gives you an idea of what a simulation looks like for a robotic arm. What we're doing here in the bottom left-hand corner, we've got what the depth sensor can see, and this is all in a simulation. So it can see two stands in the robotic arm, so it's facing straight on. And then we've dropped a can on the right-hand side stand. And then in the top right-hand corner, you can actually see it's mapped out where that can is. So it's worked out that it's object 36, it's recognized it, and it's determined exactly where it is in relation to where the robotic arm is. This then allows us to collect those XYZ coordinates and then perform that manipulation. So being able to reach out and grasp that can and potentially place it in another location. Hopefully we should see it move soon. But what you can actually do here is essentially be able to test this out in a simulation, ensure that it functions correctly and that the code functions as you would expect before then pushing it out to a physical robotic device. You can actually see the can slightly slips out of the gripper's hand. And that just goes to show in Gazebo, which is the simulation engine, you can dictate things like gravity, like inertia, mass, all of those sorts of things that may affect the ability to take an object and move it. So what we've got here is actually the physical robot that you just saw in simulation. Now this robotic device has been 3D printed. It's about 1 meter tall, and it's an open source robotic arm called the BCN 3D Moveo. It was created in Spain specifically for educational purposes and costs about $500 to build in total, including the 3D printing material, including the stepper motors and all the wiring. And what you can see here is that we pushed out the exact same code to the physical robot arm, and it's able to make the exact same motion. So we're doing a couple of test poses to ensure that it's moving correctly. And then we're able to test a pick and place. But this sort of gives you an idea of how something like this could be leveraged for educational purposes. Once again, in terms of cost, the ability to experiment for organizations or for students that are maybe engineering students has come down significantly. And also the risk in terms of learning these sorts of capabilities has come down significantly. So you're able to start off in a simulation, and assuming that you're comfortable with that simulation, you're able to then purchase the material needs to be able to build out this capability and then push the exact same code to it. So you can see there that we've dropped a can, it's recognized that can, it's worked out exactly where it is, and once again we're doing the exact same pick and place motion. And so the 3D printer to be able to print out something like this doesn't need to be expensive. This was printed on a $200 3D printer. Now for a commercial, more of a commercial use case, what we're seeing here is Ripley. This is a robotic device that was put together by Woodside Energy, who's Australia's largest operator of oil and gas production. And what it's doing is operational task autonomy. So what we've got here is a water flow system. It's a demonstration, so they're demoing basically a water flow system where they've injected an error into that system, and obviously the remote shutdown purposely fails so that they're able to deploy Ripley, which is able to perform a manual shutdown. Now, this device would potentially be in an offshore facility, unmanned offshore facility, and as a result, they'd either need to fly someone out there to be able to do that manual shutdown, or they can use a robotic device such as this that has dexterity capabilities. So what you can see is Ripley, it's rolled up to the device on its ClearPath base using a open source autonomous navigation suite. In its robotic arms, which are 2 UR5 robotic arms, it's actually running some software that comes from NASA, specifically from the Robonaut, that's used to work alongside astronauts. So it requires that dexterity. And it's going through that 4-stage shutdown procedure. It's hit the big red button initially, and then it's turning a number of levers to shut down that water flow system. So you can see how something like this would be quite useful in the event that you need to perform a manual shutdown of something in an unmanned facility. Certainly, while this does seem to take a little while, it would be much quicker than flying someone out on a chopper. And additionally, you can see how something like this would be quite useful in a situation that might be too dangerous to put a human operator near. So once that is all completed, it then provides feedback to command and control that the task has been completed successfully. So we'll now move on to the final topic of drone technology. So obviously we see it in areas of logistics and being able to fly packages to customers. We certainly see it in the areas of consumer flight. It's almost like everyone has a drone these days. In agriculture, we certainly see it from the perspective of being able to have a bird's eye view of your crops, to be able to check the health of the yield or to check for infestation, but also the ability to spray crops as well. Additionally, lately there has been the ability to even inspect fruit and to be able to pick it if it's ripe. So that's an interesting use case that we're now seeing. In the areas of aerial photography, not only from simply a photography perspective, but also to be able to inspect the condition of buildings, high-rise buildings that are hard to reach, and then in aspects of emergency response, for instance, search and rescue. So this gives you an idea of sort of where we see drone technology being used in terms of aerial photography, specifically, as I mentioned before, in building inspection. So what you can see here is a offshore oil rig. Obviously, offshore oil rigs are quite prone to corrosion and rust, which can degrade the oil rig. And as a result, you would want to be able to inspect it on a regular basis to ensure that, that you're covering off any potential risks. To be able to do that, it would be quite dangerous for a human to be able to do this, as well as potentially inspecting any other high-rise buildings like communication towers. So we're able to leverage this drone to be able to fly around it using GPS. It's able to inspect it 360 degrees. But additionally, it's able to use its video or visual capability to be able to actually inspect it up close and use edge inference, or a machine learning model that's been trained in the cloud and pushed down to the drone to be able to potentially recognize anything that looks like rust or corrosion, and then be able to send that information back to a central station to deploy someone to take a look and potentially remediate. So this is simply a simulation of that. If you get the chance, in the ARIA Expo Hall, we actually have the drone as well as, I believe it's currently doing local inference. So it's worth taking a look. This sort of provides you with an understanding of the architecture. So we have that DJI M600 drone. It's running a ROS application, which has specific machine learning libraries running as a node. And then it's got a number of Robomaker ROS extensions, which I mentioned earlier on. So it's able to send its logs to Amazon CloudWatch, But additionally, it's able to use Amazon Kinesis video streams to stream what it can see into the cloud to be stored. And then from there, we're able to actually create a front end, because everything's API driven, to be able to trigger another invocation of machine learning training on that machine learning model to then redeploy back to the drone. So we're able to constantly improve its ability to recognize things like corrosion and rust. What we can also do is, if we wanted to integrate a new capability into this robotic device or into this drone, we can leverage AWS Robomaker's development environment, build out that new capability, and then deploy that to a simulation to be able to test that out. We can do automated testing on that to ensure that we're collecting that feedback quickly. We can do regression testing to ensure that new capability that we've created doesn't affect any of the previous capabilities that we had created. And then once we're happy with the results, we can trigger a deployment down to that drone device. And so we're doing that using AWS Greengrass to be able to push it down. Once again, we're able to push it down and ensure that it's not currently performing an operation. So we can ensure that its operation is complete and that it's idle before we do that push. So this is actually one of my more favorite use cases. So Nvidia put this out a couple of years ago. And so this is a drone that's able to essentially perform what would be search and rescue. So it was only able to fly up to 1 kilometer. There's obviously battery limitations. But it's not actually using GPS to fly. It's using the trail for navigation. So it's using 2 different types of neural networks. One to be able to recognize the trail and to be able to follow it along. But additionally, it's also using object recognition to be able to detect things like humans on the path. And on top of that, it's able to use SLAM to potentially detect if there's overhanging branches that it might accidentally fly into. So you can see how something like this, or a fleet of these drones, could potentially be used for something like search and rescue. Now, this drone itself is actually running Jetson boards. They are boards that are specifically created to be able to perform multiple neural networks at once, or run multiple neural networks at once. We actually do have a demo of these boards doing something very similar in the Venetian at the Expo Hall. It's called the Dinosaur Safari. They're driving around a track and recognizing dinosaurs. So slightly different, more comical, but still the same sort of technology that drives it. It's worth going and taking a look. Those boards, I believe, the Jetson Nano started about $99 US. So definitely a very affordable platform to start experimenting with and start learning with. So if you haven't had the chance to get hands-on with the robot operating system, or if you're not currently using robotics in your industry or in your area, I'd encourage you after this to jump online and take a look at what other organizations are doing in your industry. You'd be actually quite surprised at what problems are being solved with robotics in your area. One thing I will say is that certainly it's being recognized that robotics isn't just accessible now, it's actually a necessity. So we're seeing the idea of the demographic time bomb, which is that the population is continuing to age, and as it continues to age, we're going to be facing this problem of not having enough workers to perform day-to-day tasks, and also looking after the retired population. So it is becoming more of a necessity. If you are going to start learning and start building, you definitely don't need to be a mechatronics engineer to get started. You can simply learn ROS or the robot operating system. It's the best way to start. If you're a student, AWS Educate provides a great platform for that. Otherwise, the Robot Ignite Academy is an excellent platform that provides a pay-as-you-go mechanism to be able to learn everything from drones to manipulators to autonomous vehicles. And then really try to get involved with the community. So there is Deep Racer, but as the guys mentioned, it's definitely worth taking a look at the Opensource Rover Challenge. certainly if you already have experience in Deep Racer, it makes sense to definitely get started on the open source Rover challenge. And then finally, when you do start building, definitely first thing to do is take a look at what's already been created and what's already out there. Because a lot of the time, you can simply take what the open source community has already produced and build it into your robotic application to get started much quicker. The baseline that you will be starting at will certainly be more advanced if you can certainly leverage what other people have been doing. If you are looking at using some of those AWS capabilities like recognition or Lex in your robotic application, definitely check out the Robomaker sample applications. They'll provide certainly a good boilerplate to get started from. What I'll do is I'll get the JPL guys back on stage. If anyone's got any questions that they wanted to ask from either myself or the guys from JPL. So you'll usually find that with a lot of the commercial robotic devices, you will find the models online in GitHub repos provided by themselves. And from there, you're able to spawn simulations. So for instance, the Robot Ignite Academy that provides a lot of that training, they use a lot of commercial robotic devices in their training that you're simply able to just download from GitHub and spin up in a simulation. Anything else? Yep.
Was it hitting or staining, or I mean, what was the sort of libraries they were aiming for? That's intriguing. I think I saw that on Mars, but not a lot of details provided.
Yeah. Yeah, it's interesting because it was at REMARS. So that was taken from REMARS. Look, it was using basically an image library that had labeled data in terms of the corrosion and rust that they saw. I'm not exactly sure what that would have looked like in terms of the image library, but it was labeled data that they were training it on. I believe the demonstration at the Expo Hall in the Venetian, they do put rust images in front of it for it to be able to detect or not. But it's one of those things where it's only going to be as good as it continues to be trained, which is why they're continuing to push the video footage through Kinesis video streams up into the cloud and then continuing to retrain that model.
So the question is First Robotics moving to open source Rover or other things? The answer is no. This is another really interesting project that is pretty different from what First Robotics is doing. So First Robotics and competitions and things are usually around a very specific topic. This is really intended as an education and outreach project to get people involved for the very first time. So you'll learn how to solder for the first time. Maybe you'll learn how to flash a Raspberry Pi maybe for the first time. Like it's at that level. I would say First of recent years has been a much more advanced endeavor than that. So definitely not a replacement. It's something that some teams, First Robotics teams that are also doing their first project in competition, took on this as sort of a side project. We've also seen it incorporated into some curriculums for high schools, engineering classes and things like that.
Yeah, just to add to that, one of the key points that we wanted to have the hardware and software people learn to work together. And we heard criticism from robotics education that they had no hands-on. They got all the theory, they couldn't actually apply it. So this is a way, especially for high school, to actually apply and do hands-on, experiment, fail, try it, and learn by doing. And for us, it means we will get more educated people into NASA and JPL that are willing to get their hands dirty and try things, both hardware and software. So I can address that one. So what happens, it takes about 10 months to get to Mars, for example. And if you think about the environment on Mars, it's very constrained. High radiation. If you think about a CPU or memory, if a bit gets flipped by radiation, how do you know? So it's radiation hardware, hardened computers and memory, so it's very limited. So what we do is, there's three phases. There is cruise, land, drive. Once you are cruising, we're busily writing the rest of the software because we have the team together, so it's a human factors thing too. You got 10 months to figure it out. Once you land, you don't need the cruise software anymore, so we can delete that and upload new software for actually better driving. So it's because it's so constrained, we're now working on trying to just fly new hardware, commercial hardware in space, see what the radiation can handle. We have actually taken the software that was from the Opensource Rover, converted to ROS, and then deployed it on some of our ground-based rovers that we're experimenting with. So the idea is to innovate on Earth, and eventually it gets pushed up into space, which is a more constrained environment. And when you're 150 million miles away, you don't want to make a mistake. So there's a lot of iteration that will go up there. Good question. Do you want to take
Sure. It'll be very similar to Curiosity. So before we can land a rover on Mars, because Earth is spinning, Mars is spinning, in order to communicate right now, you need line of sight with our deep space network and the big antennas. So before we land anything on Mars, there's got to be relays in space or in orbit of Mars, right? So we have a number of orbiters that are doing observations in orbit, but they're also acting as relays. So it's been set up that way ever since we landed Sojourner Pathfinder, the MER, Mars Exploration Rovers, Spirit and Opportunity, and then Curiosity. It'll be very similar with Mars 2020. And I think the data flow pipeline is very similar, with the addition that we're moving much more of the native flow to the cloud for some of those. So we have huge data pipelines that come back. We're experimenting with ground station as a service. We have these big data flow pipelines that come back, but there's also a lot of ground processing that still needs to be done. Usually that's big batch processing, and some of these workflows can really lend themselves to the cloud. So I would say the biggest change between maybe Curiosity and Mars 2020 is probably that leveraging of the cloud.
But it's a good question, because as you're getting a lot more, there's a space bubble right now, and it's wonderful. It's cheaper to launch things. It's cheaper to build things because of CubeSats, and it's cheaper now to get the data down because of ground station as a service. So you're going to get a lot more satellites. One of the things we have done is to extend internet into space, something called the DTN, Delay Tolerant Network. So we can envision that internet is just reaching out to all the satellites across the solar system and beyond. And the other thing we're experimenting with is laser comm. So we've already demonstrated that we can get 600 megabits per second back to Earth from orbit around the moon. So that's faster than I get at home. But that's line of sight optical comm. And so that's another piece that's coming. So it's a very vibrant and exciting place. And the network is truly, the constraint is the mass, trying to get it out of Earth orbit, and then the compute and the network. And the instruments are getting much smaller, largely because of our second brain, right? Everything is getting more compact, so we can now actually do CubeSats. So the network will be a huge enabler or disabler.
And to add on that too, if you think back to the Cassini slide that Tom presented, it was launched in '77. And over the lifetime of the mission, it transmitted back 630 some gigabytes worth of data. I mean, think about 635 gigabytes worth of data in 1977, right? I don't know that we dreamed that it was ever going to be possible to do things like that. And so even with hardware that was launched decades ago or is being launched today, as things evolve on the ground, our capabilities are only going to expand.
Yes.
You kind of already touched on it, but JPL's been making these robots, like you said, since before cloud, forthcoming computing. How has it changed, like the evolution of what you guys are doing? You guys already talked about it a little bit, but anything else, like either like people-wise or organization-wise?
Wonderful question. I'm going to repeat it. So I'm the, you may not believe it, but I'm actually older than he is. So I'm the old guard, he's the new guard. And robotics has been, JPL is very, very good at it, been doing it for years. But it's been a very specialized thing. Now we want the world to get involved and get hands-on and experiment that we can then fold back into our robots. So part of it is the robotic operating system. It's open source. It's a really big deal. And experimenting and doing things faster and cheaper and smaller. So we are experimenting with a whole wide range of rovers. Now Mick is a software guy building rovers. That was not really possible before. You had software people, you had hardware people, and now we see this next generation, Mick and his children, is going to be the builders. The builder community extends into robotics, thanks to things like the cloud. If you think about especially the network revolution that's happening now, you have Bluetooth 5, you have Wi-Fi 6, and you have 5G, tons of data just available wirelessly. So robotics will, obviously you don't want to wire on a robot, but all of a sudden you have more data. So you need the cloud. That's the big brain. The open source rover in this case is the middle-sized brain. The little brain is little rovers that run around that are expendables, cheap. So they all communicate back and forth. And I think it's a wonderful change for us. So we took, when we built the open source rover, Mick led it, we had the senior, very experienced rover builders as advisors, and we had interns build it. Those interns are now JPLers and brought in other interns. So it's kind of the cycle is speeding up. So you want to add to that?
Yeah, so to add to that too, I mean, it's not just the area of robotics that we're seeing a lot of benefit with cloud. So Tom and I are sort of on the IT side of the house, adding things, obviously cloud is hugely useful for data science, and data science has applications across the spectrum of different things that we do at JPL. So HR systems, right, business, travel stuff, acquisition, trying to understand so there's a lot of the human factor stuff that on the ground, even just within the JPL, fence has benefited a lot from cloud.
Certainly. So I'm actually giving a talk with Shane, the AWS guy, about ground station later on today and also tomorrow. So ground stations as a service, I happen to be an advisor to AWS because we have big antennas. And they're building these antennas across the world for low Earth orbiters, things that circle the Earth every 90 minutes or so, pump lots of data down. So we had a spacecraft called Asteria, which was the first CubeSat to actually detect an exoplanet. It's kind of done. Now we can experiment, just like Cassini, diving through the rings at the end. Now we can experiment like crazy. So we did, and we were able to. We have a catastrophic hardware failure on our antenna that tracked it. So it's nothing like a good crisis. So we were then able to track it using the ground station as a service. And it's much, much cheaper for us, and we don't have to own anything. All we had to do was take this ground software and put it in the cloud. And because the spacecraft went into emergency mode, it couldn't communicate with it. It collected a lot of data. So this station was in Ohio. Then all of a sudden we spun up another station where the ground stations were in the software in Oregon. So now we can pump twice as much data. And if you think about what that means, having antennas all over the place that you can just get on demand, swarms of satellites becomes very possible. And we had one problem where we had a hardware reset on the spacecraft. And normally that would take a couple of days to figure out. This time we did a reset command over Ohio, and as it came over Oregon, it was able to downlink the data. So all of a sudden, we're just kind of scratching the surface of what's possible, but it's a great service for us. It saves money and it lets us focus on the science of it, which is what we really care about.
I'm sorry.
Yeah.
We have another group coming in, so if you have any questions, we can take it out in the hall.
Thanks, everyone.
Thank you.
Thank you.